So welcome back. What we were discussing in our previous lecture was something known as intelligent search, wherein we introduced the paradigm of heuristics, that was an estimate to the goodness of a solution. And by this introduction of the term heuristics, we saw how we could solve the problem better. And of course, the introduction of this term introduced us to entirely two paradigms. One was the search, the breadth-first search, the depth-first search, or what is sometimes known as the uninformed search. One is completely unaware of the goodness and it tries to take a path so as to reach the goal from a source state, and the intelligent search techniques that made us the heuristics to bias their search towards better places that are possibly nearer to the goal, that possibly lead to some better distances from the source to the goal, and as such there is always a possibility to reach the goal earlier in terms of computation time, in terms of the total distance traveled. We'll later on migrate to something known as a state space approach, wherein we said that the system is in some state. From the state it can move into some bit of other states, so that may be a very good kind of graph. From one state I move into the other state, from the other state I move into the other state, and so on. I keep on moving. I've got all those possibilities of movement from one state to the other state, and eventually what I do is that my aim is to reach a predefined state, a predefined goal. One of the examples that we took was the water jug problem, in which there was 2 jugs, 3 gallon and 4 gallon, and we had to arrive at the jug of 2 gallon. Of course, a preliminary version of that graph was shown. The actual graph will keep on unfolding, representing newer and newer states. We take another very interesting problem that is known as the problem of honeybulls and cannibals. What happens is that there are 3 cannibals over here, there are 3 honeybulls over here. There is a river over here. The river has a boat over here. It can carry only 2 people. Now I need to export all these 6 people to this side of the river, making use of this boat so nobody can swim over here, such that the edge are always less than equal to C. The number of H are always less than equal to C on either side of the river at any stage of time. Because if the number of C will be large, they will over-dominate H and they will eat up H. So this is a problem that we all have been playing as flash games, as computer games, and so many times we always give this to the other students as a puzzle to solve. And then it is that they try to, these people, when they were given to solve, you try to make it random moves. You say, oh no, could not reach, start again. You again say, oh no, could not reach, this time I was so close. You start again, you again try to find out some solution based on whatever you knew from the past. Here we would be making use of the same graph search technique. Here we would be making use of the same state approach, and we'll see if we can solve this problem such that if a solution exists, it is guaranteed to give me a solution. Now remember, whenever we talk about something known as graph search, there are 2 important things that you always need to consider. One is known as the problem of completeness, and the other is known as the problem of optimality. Completeness says that if a solution exists, it will be returned by the algorithm. The algorithm on its termination will give me a solution if it exists, no matter how long it may take. But if a solution exists, it is guaranteed to return me the solution. So maybe in this problem might be that you need to have all the states explored, and the last state to be explored was the goal state. The problem of optimality would deal with, is the solution returned the best solution possible for this problem? So might be I need to optimize the number of steps from the source to the goal. In some problems it is required. that you are supposed to find out the shortest distance from the source to the goal. In this case, might be the constraint says that my boat needs to have the minimum number of movements. So is it that the solution that I return is optimal? Or in other words, there is a guarantee that I cannot find any solution that is better than the solution that my graph algorithm returns. Now some algorithms are complete, they are not optimal, some are complete, they are optimal, some are neither optimal nor they are complete. As the problem hardness increases, we would kind of migrate towards the algorithms that are neither complete nor they are optimal, but then they return you a solution. Most of the time they return you a solution in most of the cases within some limited time, because it might be that the action time is infinity. This is when we'll migrate towards the genetic algorithms and stuff, but right now we assume that we have to solve a problem that is of this nature. So the first thing that I need to do is again the representation of the state. Now any of the state my game presently is, any of the state my system presently is, any of the state my complete architecture of this thing presently is, I call it as a state. And of course, once my state has been defined, a large part of the problem is already solved. So in this case, let me say, on the first side of the river, there were H cannibals, C cannibals, and the boat was on site, let's say S, that represents a state. When I say this, I automatically mean at this side I had 3 minus H, 3 minus C, and of course the boat was on this side as the other state. So let me take some examples. 1, 2. State 1 would mean a condition H here, 2 C here. The boat is on this side of the river, and it naturally means, since the total H and C are constant, like this. Now the number of C have dominated H over here. The number of C have not dominated the H over here. So this state would be called as an invalid state. This is the state where my game ends. Let me again try to take an example. I say 2, 2, and let's say both is on the other side. So I have H, H, C, C, both over here. And I have an H here and a C here. We can take this example, the C, the H balance over here, here 1 and 1, that's okay, and both is on the other side. So there is no problem with the state over here. So my first step is done, the state representation. Obviously you can work over the state as well, that I can represent HCC and B and HHCC and B as strings. Because of course you have to make a program like a C program, a C++ program, Java program or whatever. So you will require some good data structures. These can be normal variables. Here you can take it in the form of string or whatever, which of course represents a vertex of a graph. A state always represents a vertex of a graph in which all the vertices are not known in advance. So once I know the state, I of course need to know what my source state is and what my goal state is. It is important for me to know what my source is and what my goal is. Let's say 3, 3 and 1 was my source. 3H here, 3C here, a B over here. Let me assume that a 3 over here, a 3 over here and a C over here. Let me say my goal is 0, 0, and it ideally does not matter where the boat is. But normally you would know that the last journey would have been made by some H or some C from this side to this side, so Mostly you know that the both will be on this side, so mostly you know that it will be a 2 here, but let me generalize that both can be anywhere. My goal set is this. So I know the source, I know the goal in this representation. If you have the string representation, it will be HHHCCB over here, and towards the end there will have been null over here. So I know the state representation. I formulated a kind of technique by which I can represent the state of a game in a data structure of any language that you are following. I've done that. I've tried to identify the source and goal. I assume that I have an expansion policy available. I know that I have an expansion policy that is already available. If you are using a heuristic technique, I know that a heuristic policy is already available. I do not presume that a heuristic algorithm is being used, so that's why I say that this might be optional only for the heuristic algorithm. A heuristic policy would mean that whenever any state S is given, I can find out its goodness by some value H. Whenever any state is given, I can find out its goodness. An expansion policy would mean that whenever any state is given, I can find out the next nodes that are possible. So let me say this next node possible is X. X will be a set of states possible once I expand S. And once I have the state representation, that is the basic requirement of the problem. I know the source and the goal. I know what the heuristics is, I know what the expansion is, then you can apply any of the algorithms that we saw in A-star algorithm, a heuristic search, and anything. These algorithms just made calls to these functions over here, and that's how my entire problem would be solved. So A-star algorithm mounted over this technique would be all that would be required to solve a problem. Now I will not write down the algorithm yet again, it has already been discussed. But you can see that using elements you can solve this entire problem. What would be interesting is to have some kind of graph over here. So that I can probably say that we start with 3, 3, 1. Normally you can assume that two people would be going out in a boat from left to right. So if it's 3, 3, 1, either an H moves and a C moves, either 2 C moves or 2 H moves. So if an H and a C moves, it becomes 2, 2 both on the other side. If 2 H moves, it becomes 1, 3 both on the other side. And of course, if and 2 C moves, it becomes 3, 1 both on the other side. One thing I'll have to do is that I'll have to check which of these states are invalid states. Which of these states are the states in which the H and the C, they are imbalanced. Which are the states in which the C over-dominate the H. If there is any state in which the C has over-dominated the H, I cannot move further because my game will end at that spot, my expansion policy will end at that spot, I simply need to delete that node. So by simple analysis over these number, a 2 and a 2, it means that there were 2, 2 here, there were 2, 2 here. It means almost a balanced state. If I have 1 over here, I can say that there is a 1 cannibal over here, there are 3 cannibals over here, and similarly there are 2 over here, cannibal over here, 2 over here and 1 over here. A state like this. The cannibals seem to have over-dominated over here. They seem to have over-dominated over here. If I have 3, 1 and 3, 1 would automatically mean 2 cannibals being there. Here the cannibals have not over-dominated, here the cannibal has not over-dominated, so this seems to be a bad vertex. Now I've got 2 vertices in hand in my open list. My open list has got 2 vertices here. Which one of them I need to expand? Which one of them I need to expand will be given by my algorithm. it's entirely a heuristic search, it will be the value vertex having lesser heuristics. If it is an A-star algorithm, it will be my value having lesser heuristics plus 1. That is the historical cost, that is one in both case. If it's entirely an uninformed search or the equal to the breadth-first search, I have only one over here and only one over here. So that means using a breadth-first search approach, I can expand any of these possible. But if I go on expanding further, these two states, let's say I've already expanded this, so that's one. I have a state here, I have a state here, I have a state here. Now I'll have 3 states over here and 1 state over here. Which one of them is to be expanded will be given by my search algorithm. But I'll keep on expanding this node. I'll keep on expanding some of the other of the vertex in this entire set of vertices. And what eventually I'll see is that by keep on expanding, can I reach a goal state over here? Maybe the next node to be expanded was this. So this would have given me another 3 nodes. Now there is one vertex here. Let's say 3 vertices over here. This 3 is not constant, it can obviously change anytime. A vertex over here and a vertex over here. I'll again need to expand using this expansion policy. Now the expansion policy in this case is no. Like we assumed here that 2 can travel, of course, so there would have been 3 more nodes had I taken up one edge traveling from here to here or one C traveling from here to here. There would have been 2 more cases over here. So I would have got a case like 3 to 1, 3 to 2, and I would have got a case like 2, 3, 1. I'll have to consider this. I cannot disregard that these states will not give me result. I'll have to consider these as well. So using all this technique, the graph will expand. Now we've not expanded further. We've seen how complex this graph has already become. By keeping on expanding and expanding, using the technique that is given by the algorithm. So let's say it was A-star algorithm using the technique from trying to minimize distance from source to goal, or an uninformed search trying to minimize the distance from the source, in which there will be a layer-wise decomposition, there will be a layer-wise expansion. I ultimately need to come to a state known as a goal state. That's what my expansion is. If any expansion can reach me here, I am done. So again, once the states are known a priori, once the representation technique has been done, once I have the source and the goal, I can use any standard algorithm in this way using the state space approach. The only problem lies in how do I represent the state, that is problem specific. In how do I formulate the expansion problem, that is again normally known by a series of if-else clauses that you can in your program write down this expansion policy using a heuristic policy that will again be equal to depending upon the problem. When we go into the application domain, we actually see into how A-star algorithm is used in a problem of robotic path planning. We'll actually see how do we solve this problem. That will be, most of these problems are hypothetical, they have been framed. That is a real life problem in which A-star algorithm is actually the algorithm used. Of course, one of the possible algorithms under use. So that was more or less into the search paradigm. That was more or less into the paradigm of the entire search. What we'll later concentrate upon is the fundamental of clustering. We'll see, we'll have a very little peek into the problem of clustering, and we'll see how we can handle large data in the form of clustering. So clustering is something that by definition we all know. There is a large amount of data that when represented graphically is something of this format. What I need to find out is a number of clusters which can be like this. That's what the problem of clustering is. Here I had assumed that there are 2 clusters, I can find 3 clusters, I can find out 4 clusters, I can find out 5 clusters, I can find out any number of clusters over here. Now whenever I plot this graphically, it is important to realize that there is no x and y actually over here. They can be a z, they can be a p, they can be a q. So this is a multi-dimensional space over which the clusters are found. It is a multi-dimensional space over which the clusters are found. It is not possible to visualize anything more than 3D for humans. And it's very difficult to draw 3D, so it's not possible to draw anything more than a 2D at this board here. So I say there's a very high dimensional kind of space. I'm viewing it from some angle such that these x and y are visible, and from that I can make out these two are the clusters. These two clusters can be said from the fact that they represent completely distinct region in this so-called graph. They represent some different kind of regions in this so-called graph, and that's why I can say that they can be put distinct together. Now clustering in multiple domains has multiple uses. Clustering is a tool that is used by multiple people in multiple formats. Say you're doing some kind of sampling in which you collected a large amount of data regarding the habits of people. Now you've got some 100,000 entries. You recorded the habits of 100,000 people. You want to find out how distinct people, the distinct habits of people. You have to find out how people are distinctive in nature, what are the different kinds of habits available. Now you know out of this 100,000, some 1,000 or 1,500 users may have the same habits. So when in this case plotted on a habit space, what you need to find out are clusters, and the clusters that you get will be like the distinct habits of people. Two people almost having the same habits may plot up to be almost the same in this space. Again, when it comes to working out with excessive amount of data for the machines, we normally say that my machine has a limited size, it cannot take in this much amount of data, so please reduce the data. And how do we reduce the data is again by the fundamental of clustering. Before giving data to machine, we need to ensure that the data is distinctive enough. So what do? We cluster the data into n number of clusters, and we give this n cluster centers to the machine. So a cluster center has all the characteristics that its neighbors have, and therefore using the best technique and therefore using the best kind of data, we can give it to the machine and the machine will work out. So numerous applications over here, but here we are not interested in the application domain as of now. We'll just say that there is a multi-dimensional domain, there is a multi-dimensional space. There are some points that have already been marked in the state. We have to try to find out clusters. Now a cluster will always be defined by a cluster center. So assuming number of clusters to be n, when I say I am trying to do clustering, I say that I am trying to find out cluster centers C1, C2 up to Cn. I am trying to find out these cluster centers C1, C2, C3 up to Cn. So in this space I had two clusters C1 and C2. What I am given as input is a large amount of data. Let's say I1, I2, I3, and let's say it's up to I small n. Any input here, I3, it represents an experimental data, and the experimental data will always have a set of attributes. The number of attributes will determine the dimensionality of this curve. So basically, as in any of the example I said that there was somebody who collected a large amount of data. Data would always be in form of attributes. Data would always be in the form of attributes. There was a space that was plotted where all these attributes, the corresponding point was plotted in this graph. So whenever I take any input I, that is basically the input that represents one of my experimental data. Any input I over here, it represents one of my experimental data over here. And experimental data will have attributes. So let me say the attributes in this case of any I, j were nothing but I, j1, I, j2, I, j3 and so on, I, jp, where p is the dimensionality of this graph or p is the number of attributes. And of course, a clustering algorithm needs to output these cluster centers. That is what I am supposed to output. So given a long list of inputs, each one of these input is an experimental data of a number of attributes. I need to find out a cluster. I need to find out n cluster centers. Usually n will be less than n because clustering needs to reduce the data, it does not need to expand the data. Any cluster center again, Cj, will be of the format Cj1, Cj2, Cj3 and so on up to Cjp. We were given this p-dimensional space and numerous points plotted over it as x. I have drawn it as labels x. We were given a high-dimensional space with all these points plotted up here and there. We need to find out cluster centers. So cluster center will be again point in the same space. I represent it like this. Now each one of these I over here, each one of these C over here are nothing but some real numbers over which I have plotted this graph. They are nothing but real numbers over which this graph has been plotted. Of course, at this point of time, I am not considering the classificatory attributes. I am not considering attributes like you belong to India, Sri Lanka, Australia. So India, Sri Lanka, Australia can never be plotted as a label over here. We have different techniques to handle such classes, but I will not be considering over these. What I will be only considering is that there are some real numbers. There are some real numbers, either discrete in nature or continuous in nature, but there are some real numbers so that this graph can be plotted, and once this graph can be plotted, I am asked to find out these cluster centers. Any clustering algorithm will take this set of data as the input and it will try to produce the cluster centers at this output. The cluster centers being always less than the amount of data. For simplicity, let me take an x and a y over here. These are the inputs and these are the cluster centers over here. Now there are two algorithms that we would be blindly considering, and both of them are almost alike. One is called as a k-means clustering and the other is known as a fuzzy c-means clustering. Now, the paradigm of clustering is quite large. Why are we discussing these two algorithms over here? Is that because my algorithms will at numerous times, the soft computing tools and techniques, they might make a reference to clustering, and whenever we usually make into a reference to clustering, we apply either a k-means clustering or a fuzzy c-means clustering. So let me start off with a k-means clustering over here. Assuming I am given this data, assuming I am given this amount of data over here, all the set of inputs have been given to it, what I eventually do is I take in random points over here. I assume any random C1 and C2. Again, I am only taking these two cluster centers for the sake of simplicity. A k-means clustering algorithm says that an element P is an input over here, what I had erstwhile represented by an I had represented by an ij, that is an element E over here. An element E, which would obviously be of the form E1, E2 and up to EP, that is a point in this p-dimensional space. An element E belongs to cluster J such that the distance between an element E and the cluster center J is less than any other cluster center. So according to K-means clustering algorithm, an element chooses its nearest cluster center. So if I iterate over all the elements, if I try to iterate over all the elements, this is closer to this than this because this distance is smaller than this distance. This belongs to the cluster center 1, I label it 1. This would again belong to cluster center 1, this is smaller than this. This might again belong to 1, this might again belong to 1, this will all belong to 1. This I believe would belong to 1. This I believe would again belong to 1. So like this, I find out the centers of all these clusters, I label them as 1 and 2. So what I've essentially done is that I had some class of inputs. Of course these circles are unknown at present. I do not know what these circles are. This is what I am supposed to find out. I took 2 random points. Or in a generalized case, I took in n number of random points. I randomly place them anywhere in my space. I place them anywhere randomly inside my clustering space, and what I eventually got was a set of random points. Now using the known metrics that an element belongs to the cluster whose cluster center is close to it, and that makes sense. That really makes sense because anybody belongs to a cluster that will be closest to itself. So that's what the clustering phenomena is all about. So what happens is, by this I can label all these elements with the label of the cluster they belong to. So that's what I have done. I labeled them all as 1 and 2. So at this stage, what my algorithm has done is, it has tried to form this type of clusters. A cluster over here and the other cluster over here. These are 2 clusters that have been formed initially. Now what do I do in K-means clustering? I find out the arithmetic mean of all these points. I find out the arithmetic means of all these points. So the arithmetic mean of all these points would let's say lie somewhere here. I move C1 from here to here. I find out the center of all these points. Let me say it lies here. I move C2 from here to here. Now finding out arithmetic mean of a set of elements is something that is very trivial in nature. What you would ultimately have is every cluster, let me say that xj are the set of elements that belong to the cluster J. Those would be of the form xj1, xj2 and so on up to xj. Let's say those which actually belong to the cluster center 1 was n1. Each one of these would be a point in multi-dimensional space, so they would be like xj21, xj22 up to xj2p. These are points in the x-dimensional space. All I need to do is that attribute wise. Sum it up attributes wise and take out the mean. So when I sum it up attribute wise, I take out this mean, I basically get up the cluster center C1 and C2. Of course, whenever I say distance, I can mean a Euclidean norm, I can mean a Manhattan norm, or any other norm for that sake. When I say mean, I usually mean an arithmetic mean. That is what is used in the k-means clustering algorithm. So there is a C1 and C2 that I get after this entire procedure. Now this represents one iteration of the algorithm. After one, I started off with random C1 and C2. In one iteration, what I do is that I, making a note of the C1 and C2, I classify all these class labels, I allocate all the element subclasses, and then I move C1 and C2 to their means. So I got a modified C1 and C2. Now it can be seen that the centers that were very abnormally placed here and here are now more normally placed. They are closer than the ideal values that happens to be somewhere here and somewhere here. They happen to be much ideal somewhere here and somewhere here. So what happens when I do another iteration of it? Let me say this was the actual space that I was working upon. Let's say this was the actual space. My C1 is located somewhere over here and my C2 is located somewhere over here. I again try to cluster these. So it's all 1 over here, it's 1 over here, and it's 2 over here. You can eventually see that the mean of this and the mean of this, these are the clusters, new cluster centers that have been found. C2 will eventually shift up a little this side because of the mean over here. This is where C2 will now lie. My C1 will again shift over here. These, as per these elements, values, more are located at this side, so C1 will shift over here. So if I trace C1, it moved from somewhere over here, from the first iteration, to somewhere over here at the second iteration, to somewhere over here in the third iteration. It's moving up towards its ideal value. And C2 moved from somewhere over here at its first iteration, from somewhere over here at its second iteration, to somewhere over here at its third iteration. Another thing that can be seen is that firstly they are moving towards their normal values, the ideal values, and secondly the distance is reducing. So if I execute it 10 times, my task is almost done, they almost line up over here. If I do it at the 11th time, there will be a very small change. If I do it 12th time, there will be again a very small change. If I do it 1000th time, there will be hardly any changes. That's why I said my algorithm stops. I almost found out the actual cluster centers. So this was like how I can perform clustering using the k-means algorithm, using the k-means clustering algorithm. I'll write down a very short code snippet that does exactly the same thing. It tries to cluster. Whatever I have spoken would eventually be repeated as a formal algorithm. So my inputs are, let me say, I to this algorithm. That is a collection of elements of the form I1, I2, I3 up to I small n. My outputs are a set of cluster C1, C2 up to C capital N. My algorithm using this input state S, what it eventually does is that it assumes a random set of n p-dimensional array numbers. This is what I assume will give me random C cluster centers. Then for every element E in cluster I, all I do is find cluster J to which E belongs. That is using the minimum distance. What I'll do ultimately for E, I'll find out its distance from all the centers, all the n number of centers over here. I'll find out its distance from C1, I'll find out distance from C2, I'll find out its distance from Cn. Whichever gives me the lowest distance is what it belongs to. Is the label what it belongs to. Another way to write would probably be that label of the element E is marked to be J such that the distance of E to Cj is less than the distance of E to Ck for all k not equal to J. That is how I find out the label using the minimum function, using the minimal kind of attributes. Now once I find out this element, what I say is that for every cluster center Cj, the modified Cj becomes the arithmetic mean of all the cluster center. So I say it is summation of the element, the input Ik divided by the total number of elements in Ik divided by total number of elements in cluster K, and this summation is such that label of Ik is nothing but J. So I try to find out the arithmetic mean of all these. I update this up. All I need to do is this represents one iteration of the loop. This is when I try to work over with the centers and I try to designate labels to them, and based on that I try to relocate the centers which were random at initially. I just need to say while and some stopping criterion which is not met. Now what the stopping criterion is, normally I would take in two kinds of stopping criterion. Any one of these is that I'll take. Firstly, the first stopping criterion that is normally taken is the cluster, the movement between the cluster centers, the cumulative movement of all cluster centers. Let me say C at time t plus 1 minus C at time t, the norm of it is less than a threshold value. So I can say that the cluster centers do not move at all. They've almost become stagnated. Eta is a very small value. So clusters are not at all moving in nature. So if I say if this happens that the clusters are not moving in nature, let me say it was Ci and a summation over here. The cumulative movement in clusters, if it is less than some eta value. The second thing that I can normally say is that if my quality of solution, if I receive some threshold of quality, I say that my cluster center is done. If I receive some kind of threshold quality, I say that the kind of solution that I received is fine, that is enough, that will do. Now quality can be defined in multiple parameters depending upon the algorithm. Depending upon your requirement, it can be defined in multiple parameters. What I normally would take out quality to be that the clusters that you make, they need to have a very high interclass, very low interclass separation. When I say I need to have very low interclass separation, is that I mean that the distance of any element towards its cluster center, when I sum it up for all these, this distance should be as less as possible. That is what the fundamental of clustering algorithm is. So I'll draw a bit of neater diagram. I say these were the cluster centers. These are the ones that after final execution of the algorithm belong to C1, and these are the ones that after final execution of the algorithm belong to C2. I need to say this A plus B plus C plus D plus E plus F plus G plus I plus J plus K plus L plus M plus N plus O. So summation A to O, the distance of any element E when computed from its cluster center Ci, I is such that E belongs to the cluster I. This number has to be minimal, and if it is less than eta, any other threshold, I say my clustering should stop. I say that my clustering can entirely stop. The other thing that can normally be considered is the intra-class separation that needs to be as high as possible. I say distance for this cluster from all the elements from all the other clusters needs to be as high as possible. Sometimes even a ratio can be taken, but I stick to the inter-class separation that needs to be as less as possible. So formally my quality of solution would mean that when summed over all the elements E, the distance of EI to the cluster center J, this distance has to be the minimal. Now when I say this, I have said that E is nothing but any element of I, and J is nothing but the cluster to which E belongs. So I simply say it is the label of E, and that's all. That's my work would be done. So that is what would be the K-means clustering algorithm. That is what I have it as the K-means clustering algorithm. It's entirely an iterative algorithm. It is entirely an iterative algorithm. As you can see, the cluster center keep on moving, and the degree of movement, it becomes lesser and lesser as we go upon. Now one thing that you would notice is that we had a random start. Normally what would happen is that you start up anywhere in any combination, the clusters will always take their ideal values. Of course they can be that C2 could have gone here and C1 could have gone here, so any permutation is allowed. Normally you would have that all the clusters taking the ideal values. Of course, there are multiple scenarios in which the clusters do not take in values. There are scenarios in which they take in completely opposite values as well. But that is usually the case when my data is not evenly distributed, in which there happens to be some problems in computing the actual cluster centers. But if I execute this algorithm repeatedly, for any combination of centers, for any combination of random placement of centers, they should reach their ideal values. The number of iterations will depend on how these are placed. For some, it may be possible that after a couple of iterations only they reach their good places. For others, it might require a bit longer, but ideally it should happen that all algorithms reach their ideal, all centers reach their ideal values towards the end of the algorithm. We'll apply a very small change in this algorithm. Everything remains the same, and we'll convert it into a fuzzy C-means algorithm. Again, the inputs are the same, the outputs are the same, the cluster centers that need to be found out. What I eventually do is that if it's a fuzzy C-means clustering, all it means, because of the term fuzzy here that we would be seeing in later stages of time what does fuzzy mean, but for discussion at this moment, it simply means all elements belong to all clusters. So I cannot say this element belongs, an element E belongs to cluster Cj. I have to say an element E belongs to C1 as well. At the same time it belongs to C2, at the same time it belongs to C3, at the same time it belongs to C4, and at the same time it belongs to a cluster Cn. Of course, there is a concept concept known as membership. An element E belongs to the cluster Cj only to some degree, usually measured between the interval of 0 to 1. So that is like what we would eventually be learning in fuzzy algebra. That's like saying you are 80% correct and 20% wrong. So till to a degree of 0.8 you belong to the class correct, and to a degree of 0.2 you belong to a class wrong. That is like saying the temperature is hot to a degree of 30 to a confidence value of 0.9. So all these things that are that's fuzzy algebra, but my only change that I'll make is that Cj, the element E belongs to the cluster center Cj up to some degree U. If this degree is closer to 1, it means that it almost lies to Cj. It means it is almost a member of Cj, and that always means that the degree of membership to the other elements is other cluster centers is fairly low. If I say it belongs to C, it has a degree of membership of 0.05. It means it vaguely belongs to that cluster. It vaguely belongs to that cluster. It actually might be very close to some other cluster. So there will be a degree of membership that we'll study in more detail when it comes to the fuzzy algebra. But fuzzy C means clustering. It's all about the introduction of this degree of membership. The algorithm remaining quite the same. Now the degree of membership of any element E to Cj is inversely proportional to its actual distance from the cluster center. So if in the same example I say this was an element E and this was a cluster center C2, if this distance is very large, the degree of membership is very low. At the same time, if this was a cluster center at C1, if this distance is very small, the degree of membership will be very high. There's a normal algorithm there's a normal relationship that I've applied, and that makes sense. The element E, its degree of membership to this is very large and the degree of membership is very low. So this should have a very large value, this should have a very low value. This almost lies at C1. Remember, C1 is here and E is here. So this distance is almost 0. So degree of membership will be very high, and this distance is very large, so degree of membership would be very low. One thing that we maintain is that these values are always normalized. So whenever I find out this degree, I would always say that they need to be normalized. Normalized means that summation of this value should always be 1. When summed over n. That means if they are 5 clusters, there is an element E over here. This is the multi-dimensional space. There were 3 cluster center. Here there were cluster center, but only 2. I have increased that to 3. If there were 3 cluster center, these are the distances A, B, C. The membership will be 1 upon A, 1 upon B, 1 upon C for C1, C2 and C3. I mean that I need to normalize this. So my actual membership values would be such that the sum of all these values should be 1. So that 1 upon A plus 1 upon B plus 1 upon C should ultimately come out to be 1. I need to divide it by certain factors so that this thing needs to be true. And how is the normalization carried upon is a natural fact that you apply this over the summation of these actual values. So what I do is that the normalized value of any E to Cj will be nothing but the unnormalized value of any E to Cj divided by the summation of all of any U element E to Cj. sum this up, it will be summation this, the numerator gets common, this gets cancelled, the sum comes out to be 1. So I calculated the membership, I calculate the normalized membership. All I need to do now is to try to modify the cluster centers in such a way that all I need to do is, using this membership, I need to calculate the cluster centers. Now I need to modify the cluster center Cj. The cluster center is again a simple arithmetic mean. So all I need to do is summation over all elements E that belong to the cluster that are in I. I need to say that it is exactly the arithmetic mean. So I say it will be the summation of E. Now one thing I need to consider is the membership value. They belong to different membership value. So in place of normal arithmetic mean, the only change I apply is the weighted arithmetic mean. So it has been taken by some weight over here. The weight is the membership function, and of course it will be summation of Cj over here. Normally I can have this being raised to the power n and this being raised to the power n, where n denotes the degree of falsification. So I can see a very normal arithmetic mean being taken over elements E. Now in my previous example on k-means clustering, I had iterated the algorithm over all the elements that belong to that cluster. Here, because all the elements belong to all cluster, I iterated over all the elements I. I iterated that exactly over all the elements I, weighted by the membership degrees. I just introduced one thing, that I have weighted them by their membership degrees over here. And of course, this is what would, when I weighted over membership degrees here, I always need, because I am taking the mean, I need to divide the factor by the summation of all weights. So again the same thing happens as an algorithm. I take a random Cj, I take all the random Cj, the same algorithm, so they will be placed at random positions over here. I find out the membership values of each element to each Cj, so there will be a matrix that I will get of membership value of all the membership values of each element to each cluster centers. The next thing that I applied is that I normalize these membership values by this. After I normalize, I modify the cluster centers. Once I got the modified cluster center, my membership values will change. If my membership values is staying, I have to again normalize it. If I again normalize it, I will again change the cluster center. So if I add just C is again some random points over here, I start from here, I go up to this point, I calculate the membership values, I normalize them up, I change the cluster centers, I again go, I find out the modified membership value, because if the cluster center change, the membership will change. This is my entire algorithm. It goes all in stages. In my iteration, I'll have step 1 this, I'll have step 2 as this normalization, I'll have step 3 as this modification, and it will go on and on, it will repeat itself. So that was the other type of clustering that we were dealing with. That was called as the fuzzy C-means clustering, in which the only change applied was the introduction of this fuzziness. We'll deal more with it when we come towards later sessions, and they will again start off with a wave function pattern of the basis of optimal.